will call now outside world as a jungle. So now all of you who are in the institute, right? You are in a zoo. That is the most safest place, where you are taken complete care by your teachers and your management. So you are in the best place or best phase of your life. The outside world is a jungle. It's very, I would call, it's, they call it as a rat race or highly competition. So in that kind of world, how things are seen is something very important, for someone who's going to enter the industry or the outside world for their career. So outside world sees everything at a very high level. Now, if you see any product at a high level, right, there is this application development, there is this software platform, then there is this hardware. Now, these two have to coexist, and these two have to coexist. Only if this principle is taken care, then only from an engineering perspective, the product is a success. Okay, so I'll give you an example. Uh, See, few years before, there was an hacking attack on Intel chips. The hackers were able to actually get into the Intel chip, and they were able to access the registers and all these things. So what was happening there was software platform and the hardware, that coexistence was not good. So what happens is, right, if you want to access the hardware, only through the software platform you can access. So or else the hardware is nothing but like a sand. The chip is made of silica, right? Sand is also silica. It's nothing but a sand. The sand which is not usable, I would say. Okay. So this interface, where the software platform and hardware interface has to be very secured. Okay, if you want to access some register, only certain applications as is allowed to access. Not all applications can access the hardware. Some operating system, no features can access the hardware. Okay, not a small C program or a Java application. No, it cannot access the hardware. So there was a security loophole. Because of that, that hacking was possible. So I think it is called as some kind of a meltdown. Okay, you can just check it online. Okay, now we'll come to the second interface. Okay, so this application and platform. So here, right, you can take the recent. No, there was some attack on Microsoft systems. No, lot of flights got cancelled. Even laptops, no, they had this blue screen error. So they made some mistake. No, I don't want to get into the mistake. The mistake was very simple. They were accessing a null pointer location. As simple as that. That was causing a crash continuously in a loop. Okay. So the thing is, this application and software interface has to be perfect. Okay. So this is another thing from an engineer perspective that is very, very important. Okay. So these are things that are very important, and we have to see from a software platform development in general. Okay. Yes. So okay, now I'll get into the details. Now, right, from a engineering graduate perspective, what should I know to do this platform in development? What is actually platform development? At least know, if I go to a shop, supermarket to buy, I need to know what is I have to buy. If I'm hungry, what should I buy? If I'm for the next 1 week, what I have to buy? What is needed for cooking? I need vegetables, rice, something like that, right? So if you're going to do some product, you need to understand what is there in the platform development side. Okay. See, the first thing, okay, from a BTech guys or MTech guys is, you need to be very good in linked list. You need to understand what is middleware. Okay. What is an operating systems? Okay. How it works. Okay. Then inter-process communication mechanisms and something similar to these lines. So these are the subjects or area of expertise that is actually needed for a software platform development. Okay, the beauty of these things is, right, this linked list, all these things, they are independent of an application. The linked list concept is going to be same in a C program, same in a Java application. Whatever application you write, it's going to be same. It's going to be the same Windows or Linux operating system, Ubuntu operating system, or your mobile you take an Android operating system. Okay, it's going to be same. Over that, you're going to do lot of applications are going to run. Okay, the use cases are going to be different. Okay, that is important. We should understand these are the fundamentals. See, once we get out of the college, right, we might go into different job streams. Okay, so initially I go into some, let's say I get into some cloud apps development. I might not use no a lot of these OS concepts, but eventually when you grow in the industry, okay, when you start become a lead, when you start to build a team, when you start to go and talk to customers to build a product, to understand the requirement, then the fundamentals of no electron EC, triple E, computer science, whatever you learn, no, they are going to matter a lot. Probably once you graduate, you might not use it. It doesn't mean that the education which we do is useless. It is very, very, very important. Okay. At least from my experience, I would say I have done my syllabus had civil engineering subject, it had mechanical engineering subject, it had electrical subject. Okay, but now I understand when I talk to a lot of people, no, the same software a civil engineer will buy, his requirement or his use case is different. The same goes for, but to understand what they talk, no, we should have the fundamentals of different engineering domains. Okay, similarly, if you take application development in a software, the fundamentals of a computer science is very, very crucial. Okay, so this is something which we have to be very solid. We have to understand in a layman term. It's not about getting the best mark, solving the best problems. If a first year guy, or let's say our parents or grandparents ask us what is operating system, we should be able to explain in them in the very simpler terminologies. If we are able to do, then only we have got the expertise over this. So this platform expertise is very important for people who are going to work in any technology or any domain. Okay, because once they grow, their role is going to change. When you change the role, you have to know about a lot of things around. Okay, that's where. So so with that comes the advantage here is these things they don't know about application. It can be any application. So that is something we have to understand. A knowledge which we gain today is not going to change over a time. So anyone who is going to work in platform development, he is not going to do new learnings. Okay, only thing is for a new technology he might learn. Okay, suppose you take when I studied, no, like now you have ML. It's a hot topic everywhere, ML. When I studied 15 years before, J2E was the hot topic. Now J2E is not visible. Okay, but the operating system which I studied in my BTech third year, still I'm using it today. Till today, I'm using interrupts, I'm using inter-process communications, I'm using MLOG, CLOG, everything. It is not changing. So that is an advantage here. There is nothing wrong if you study something extra. This is not going to change. So it is the worst case, you might not use it. The best case is you will use it. And most of the time, if your industry more than 10 years, you're going to use it. Okay. The third thing is with respect to platform development is the choice of software platform will have an impact on system performance. So what kind of a software platform you're going to design that will impact the system performance, but functionality, it will be the same. Okay. For example, you take a software platform, okay, that is developed for our laptop. In this laptop, right, if I run some GPU, no, image processing, image decoding applications, or the deep learning ML, all those applications, it might work, I will say, but performance will not be as expected. Okay. So with respect to software platform, whenever we design, no, we have to make sure it will work for different use cases or different applications or different hardware designs. Only thing that might differ is the system performance. Okay, that is something which we have to keep in mind. Okay, so now with respect to platform development, now what and all things that will fall here? No, something someone wants to is eager to know or learn, no. So you have to understand the best OS for platform development or learning is Linux based OS. So you have Ubuntu, Debian, lot of CentOS variants, Amazon. Everyone is nowadays coming with a open source, Linux based operating system where you can learn everything, you can do anything, you can start your own company. A lot of things with respect to Windows. No, I'm not blaming them, but from an engineering or a learner perspective, nothing much we can learn from Windows. Okay, it is very good in terms of usability for end users, but from an engineering point of view, we have to see if you want to have a career in this, no, or if you want to know about this, you have to know about Linux. I mean, no means it's an ocean. Something we should be starting to know about it. What is that? How it works, like that. So then we have something, the second class of operating system called as real-time operating systems, RTOS. So Zephyr, FreeRTOS, so these are some of the famous RTOS that is going on market. So this RTOS is needed, particularly when you go into this IoT embedded systems domains. Okay, this Linux, no, these are standalone operating systems. These are needed, for some controllers or for laptops, desktops. All these places you need a Linux. Then actually I forgot to mention there is another class of operating systems called as server classes. Okay, there is something called as BSD Linux. Okay, so Berkeley Software Development Linux. Those and all go into a deployment in servers. Okay, so you can see a uniformity here. All these are operating systems. Okay, then there is uniqueness here in terms of performance. RTOS will have your compute chips. I'll call it as compute chips. Compute means doing some computational operation. Okay, it can be anything. Okay, generic term we'll use is compute chips. So the compute chips power is very less when it works very less, then you generally use it is kind of an expected level in terms of 2 gigahertz or 1 gigahertz. You use a Linux or a Windows desktop operating systems. Okay, when the compute power is huge, that's where we use these. For example, the cloud computing things. All this goes to a cloud, where they do some computation, they give the results. So all those cloud centers, you will have these server operating systems. So as an engineer, someone who wants to have on this, they should have some knowledge of these things. You take a small concept in operating system, you just need to understand how it works in our how it works on standalone operating system, how it works in server. Okay, very simple. You take a semaphore or a logs or interrupts, how it works. That is what the learning is. Then the next thing for platform development is there's something called as cross compilers. Okay, so we have to understand, we write a program. So you do a compilation, you get a .exe file. Now, this .exe file is it created for on x86 or ARM or any other hardware, some hardware, no? So ARM is a company, Intel is a company. There will be another companies also, which might not be visible to us. Now, the thing is, what is this cross compilers? Compiler is something which will convert our high level or an assembly language into a binary. You give a assembly file, you get output as a exe, which is nothing but zeros and ones. Okay, now I have manufactured one ARM chip. Okay, that is the first ARM chip, for example. Now I have only Intel machines. Now I will put one load on exe on the ARM chip. The exe I'm loading on ARM chip has to be compatible with ARM instruction sets. So how will I do that? That's where this innovation of cross compilers came. Cross compiler is nothing but a compiler that will compile your C program for a different architecture. Okay, you can have an Intel machine and you have install a cross compiler that will compile your C code for ARM machine. So that's how this works. So this cross compiler is something which we need to be aware of, have some understanding. Okay, now for a first ARM chip, okay, you used an Intel machine to compile the exe. No, for the first Intel machine, how it was compiled? Can anyone say me? So yeah, you can just raise your hand and you can, if you can answer. It's just common sense, I will say. Can someone say that? Chat. Uh, okay, let me tell you. The answer is very simple. For the first machine, they wrote in hand, okay, zeros and ones, which the hardware will decode and it will run as a meaningful instruction. Okay. So that's a huge history. Before this, there was something called as punch card. Okay. So that punch card, they'll punch the zeros and ones, they'll insert it. Okay. Then the computer will pick up and it will run. Okay. So once the first Intel machine that is powerful came out, from there the high powerful machines got developed. Then came the cross compilers, all this histories. Okay. The last one, okay, with respect to platform development is we should be very uh, good, or at least have understanding of what is a board schematic. So there is something called as a board diagram. Okay, for any compute product you take, there will be one diagram. For example, house, you have some diagram, right? The civil engineer will give you a diagram which says this is a kitchen, this is a hall, there is a staircase here. Like that, there is a diagram for this board, no, motherboard that is getting manufactured. We should be able to understand that board diagram. We should be able to see that board diagram and say, this is the sound port, this is the Ethernet port. Okay, this is where the CPU stands. Okay, this is an essential qualification to actually, I would say, to know the to do platform development. Now, all the six things which I listed, right? A computer science graduate will definitely understand or try to figure it out. Any institute you take IITs, NITs, whatever you take, most of, I would say, not all over, most of the institutes, all these things are covered. Now, this reading board schematics and how to identifying interface is something that is not covered in covered for computer science graduates. So this is something, no, which they themselves have to figure it out or do some experiment, use a enthusiasm to talk to the professor and learn from them. The nice thing about US and certain universities, in Euro, in the West is, right, they have a department called as electrical and computational sciences. So what happens is that, right, they try to bridge both electrical and computer science, thereby, right, there's a very good chance of a person actually doing and, reading this board schematics and identifying the interfaces, some some basic things about the hardware. Okay, the otherwise also the electronics guys, they will also get chance to get into lot of software side. Okay, so this is something that is essential in platform development. Okay, as I mentioned, for new age technologies, the thing is you have to identify which kind of technology or product. Similarly, how the board schematics will be. Okay, what are the components that has to be. Okay, it is all based on performance. So if someone has any questions, I just hear a noise. Okay, so this is about no platform development in detail. Probably at the end we will have questions where we can actually get into each topic if someone wants to ask any questions. Okay, so probably I'll give 2 minutes. So if you have any questions, you can ask. So yeah, students, have any questions or you want to understand something? Fine, I'll continue. Okay, so the last thing is, right, as I mentioned about board schematics, we should be also good enough to understand the hardware HLD to actually make a choice on what kind of a software we have to do. So this is a sample HLD which I have. You have, no, this arrow line is called as a bus. Okay, bus is nothing but some electrical wire through which you connect lot of hardware components. Okay, so you have a RAM, flash, CPU, DMA controllers, lot of stuffs are there. I'll get into all these things. See, the most important thing for us to understand here is there is something called as low speed bus, something called as high speed bus. So high speed bus actually has components that can do data transfer in terms of GB. Okay, for example, you take your cloud, no, applications or server side applications where data transfer is huge, or you take your internet, no, you download movies or you stream YouTube videos, that data transfer is huge. So in those scenarios you need to have an high speed bus. If you're going to go on high speed bus, based on that, no, you have to choose what kind of an operating system we are going to use. Okay, what kind of driver we are going to use, all these things, no, we have to decide. So low speed buses are something like I2C, UART, no, all those are something kind of low speed buses. Yeah, so whatever we have seen now, right? So I have tried to cover it something which is, generic or usable across different uh, types of, classes of devices, over the time. Now I'll try to cover two important topics. Okay, it's an introduction. I'm not going to talk about each thing. See, which is very essential if someone wants to work on some newer technologies. Okay, one is called as DMA, direct memory access. Then there is another thing called as PCI bus, PCI switch. These two things are very important and they are very powerful now because of this AML and video decoding and we see no full HD movies or Blu-ray movies, lot of no beautiful images or beautiful videos we see. No, all these are possible because of this DMA and PCIe. Okay, so what happens is here, right? Before going to this, I'll just tell you where exactly this DMA comes into picture. So here we have this high-speed buses. Okay, so one of the high-speed buses is actually a PCIe. Okay, PCIe can do data transfer at a higher data rate. You can transfer data back and forth in terms in GBs. Okay, then also you have something called as DMA that exists just before the high speed bus. Okay, so DMA is something, no, where data can be moved from this RAM to this memory on this right side of the PCA at a very quick speed. Okay, so you don't need to go to the CPU. All these things, no, are not needed. Directly, you can just get the data move here. Okay, so that is where, no, pictorially, this is where your DMA and high speed DMA and PCI exist, and these two technologies or hardware components and their corresponding software platform development are the reasons we are talking a lot about AML, Chat GPT. No, there are a lot of good things happening up with this AML. There are a lot of bad things happening. But how we are able to do things that are unimaginable just few years before is because we are able to get so much data out and we are able to process so much data and come with an inference in a very short duration. Now, how all this is possible is because of this high speed buses or interfaces where you can send lot of data back and forth. Okay, so that's what is DMA. So what you have here is generally called as a host. So whatever you connect here, no, to the PCI, we call it as an accelerator. Accelerator is nothing but whatever your existing host CPU does, accelerator will just speed it up. Okay, it can do the same thing in lesser time duration. Okay, that is what is an accelerator, right? Okay, so this understanding is very important because I'm going to use certain terminologies which is necessary to understand those terms. No, you have to understand this. The left side to me, right, or the right, left side is the host, and the right side is nothing but the accelerator side. So in between, you will have this DMA and PCI. Okay, so I'll just give a brief intro about the key to the new use cases which we see all around. Okay, so we have to understand this DMA. It is nothing but a direct memory access. Okay, directly an accelerator can go and access the memory in the host CPU. Okay, any accelerator here can directly access a memory in the host CPU. That is, a RAM is a memory here in this diagram. They can just go and directly access by ignoring the CPU. CPU is actually a controller of this complete system. But I will ignore this CPU and go and access the memory here. When I mean access the memory, either it can copy data from here and put it here, or take data from here and put it here. Can do a read or write operation. Okay. When I avoid CPU, what I get is I will avoid lot of processing time. Okay, it will eventually end up about moving data from one place to another. Okay, it is the CPU earlier was kind of a master. I am just bypassing this master and directly going and talking to the slave. Okay, that's what is more of a DMA thing. So you have something called as host to card, card to host, and card to card. Okay, so this DMA need not be between host to card or card to host. It can also be between two accelerator cards. Okay, suppose I have two accelerator cards. If I want to transfer memory across this accelerator card, there also I can put a DMA. Okay, so this DMA is so much useful so that we can transfer data in terms of GBs. Okay, so now how this DMA works at a very high level, how it works is the CPU is going to program the DMA engine and say that, boss, you send data from card to host or host to card, okay, or card to card. Once the CPU programs that, then the DMA engine will automatically start the transferring of data, right? So this is how simple way DMA works. Okay, so I hear some noise. Someone wants any question? Okay, so where I left is how this DMA works. Basically, CPU tells the DMA engine, you start transferring data from X to Y or Y to X. Then DMA engine will say, yes, I will transfer. It will transfer the data and it will tell the CPU, I have done transfer. That's it. It's as simple as that. Okay. Now, what is the advantage of this data transfer is, one thing what we see is that we are avoiding the CPU. Okay, it is not only about avoiding the CPU, we are also enabling low power modes. So when I say low power mode is, right, power we should understand. See, we should understand, I have mentioned you two architecture, one is ARM, another is x86. Why I mentioned those two is, there are other architectures also. For example, something new on the block is RISC-V. Then you have something called as MIPS. See, this x86 and ARM has an interesting story. Intel chips are found in desktops, laptops, everywhere. But very few Intel chips are found in mobile phones. Why? Both are corporate entities. They are at some level which we cannot think. Okay, in terms of power, in terms of money, in terms of customer reachability, everything. Okay. So okay, we have ARM chips, which is everywhere in mobile phones. Okay, so why these Intel chips are not in mobile phones? There is a reason to that. Okay, the reason is, as I mentioned here, this low power mode is very, very important. The ARM chips works at a lower power. When I say lower power means the heat, it is going to consume few watt of power. When you consume few watts of power, the heat energy that is going to dissipate is going to be very less. Okay, but if you take your laptop, the heat dissipated is so huge. Okay, even desktop, you cannot put your laptop running, your AI after a few minutes, I would say. It patience in your mobile, okay? But it doesn't heat up because chips are designed for low power. That is because low power has lots of use cases. Okay, see, the low power use cases are huge such that one of my friend from who did BTech in mechanical, he did masters and PhD in mechanical engineering and he is working in Microsoft. That is because these software companies have huge servers where no lot of cloud applications run, lot of AML applications run, but they need this mechanical engineering knowledge to basically reduce the power. Okay, so when the industry is moving towards different engineering domains to reduce no the utility of the compute chips or the reduce the power of the compute chips, it makes mandatory for us as a software engineers to give solutions which consume low power. Okay, so that's where no when DMA comes into picture, what happens is the CPU is not in picture. Now this CPU controls timer, flash, low bus interfaces, all these things. Okay, when CPU itself is put into sleep state, all these guys are also into sleep state. Only the DMA engine here, this accelerator here, and this RAM memory are powered on. So we are actually reducing power apart from transferring data. Okay, so it's more like a double gain here. Okay, so DMA as a technology or methodology of data transfer actually gives an advantage of reducing the power consumption of the compute chip. Okay, the next one is PCI. So this PCI buses are something like this. If you open your desktop, right, you can see it. So these are PCI lines. There are a lot of PCI lines where people put some people who are interested in gaming, they'll put their graphic accelerator cards. People are who are interested in having high data transfers over Ethernet, they might put a new Ethernet card here. Okay, you can put memory cards also here. So the advantage of PCI is it provides a quicker read and write speeds. You can transfer data in terms of 16 Gbps, 32 Gbps based on your PCI generation. Okay, PCI generation has 1, 2, 3, 4, 5, 5 is something that is very latest, where we can transfer data. I think 32 Gbps or more. Okay, so this PCI is another thing that actually makes all this AI, ML, IoT, cloud, data mining, data analytics, whatever you say, those things as a possibility. All these concepts were there several years before. Okay, several generations before. They were in a different form. Okay, but why it is realized now? Because to realize all those dreams or ideas, you needed a greater hardware, powerful hardware. All those are happening just now. So all the dreams are getting realized now. Okay, so this PCI and DMA are very key to realize these dreams. Everyone actually should know what is PCI DMA, whether you are working on platform side or not in your company. Okay, they make a lot of sense. Yeah, now we'll jump into the firmware development. See, this platform software actually has something called as firmware. Okay, firmware is the one which binds the operating system to the hardware. Okay, so it's a small layer where we write small C programs or assembly code which will actually write the registers, configure the different hardwares. Okay, to work in a particular way. Okay, so it's a very hot area. If anyone chooses this as a career, it's very good for them. It's going to give lot of dividends over the years. The more you are experienced in firmware, the more the value for someone in the market. Okay, getting a firmware engineer is very difficult. As I mentioned, it's a very technical area. Uh, no, you should be very strong in fundamentals and basics. You should be good in understanding other domain subjects. You should be able to understand, no, talk to some electronics person or a mechanical person to understand a lot of things. Okay, it requires a lot of common sense, and common sense is not something simple, I would say here. When I mean common sense is you have to understand things in a simpler way. Okay, you have to understand things how everyone understand. Okay, so that is the critical thing. Okay, and the challenging here is debugging the issues. If anything happens wrong, how you debug, that is very deep. That is the challenge here is. Okay, now I'll just cover up for the students what actually you should be learning, whatever you have learned that you will be using in firmware development. First thing is you should be very good in arrays and linked list, because any hardware software interface you will find lot of buffers through which data is actually transferred to and fro. Okay, so these buffers are created using arrays and linked list. So if the buffer size is fixed, an array is used. If the buffer size is changing, they use something called as linked list. So there is a terminology called as buffer chaining. Okay, so linked list and arrays is a very simple topic, basic topic in computer science, which is very crucial for all of the new technology and compute machines that are working. Okay, for example, whatever this Microsoft issue we saw last month is because of a null pointer access. Okay, whenever you use an array, you should do an array out of bound access. Whenever you use a linked list, you have to do a null check. So that is the thing about firmware development. The next thing is just a minute. Then the thing is, if you're working on OS kernel or routing algorithms and all, right, you need to be know about hashing, trees, and graphs. So this is where actual firmware development happens. Okay, then if you see how this works on modern technology is, so you have a, so I'll just take a question. So if anyone has any questions or they want to ask some questions. Fine, I'll just take it forward. Okay, I think we have just 2 more slides. Okay, so how this modern technology works, from an engineer perspective, we have something called a single instruction, multiple data. So whatever instruction here we have on the left, right, the single instruction runs for a single data. When we have a vector representation, you can have a single instruction running on multitude of data. Okay, so that is where we get the speed, performance, all this image rendering or AML. That's how it works. So someone who wants to work on AML, they should be very good in vector algebra, good in matrix operations, and good in actually realizing a simple thing in terms of a simple operations in terms of matrix and vector operations. Okay, so the next thing is, what are the compilers that are needed to use this new age hardware? So there is something called as model compiler. I think everyone who have worked on AML, right, you would have used this model compiler. So what is this model compiler is? It basically is nothing but it is a realization of your hardware. You have an hardware. I want to use this hardware and realize that. For that, there is a software that is called as a model compiler. This compiler is actually totally different from the compiler which we use to compile our C program or a Java program. Okay, although it might look simple. Okay, then you have something called as graph compilers. Okay, so whatever I'm talking here, right? All these are the job opportunities that is open in the market. If someone is good in understanding model compilers, how to operate the model compilers, that's where no the job opening is. Next is graph compilers. Graph compilers are nothing but whatever models we see, right? People call it chat GPT is a model, GPT-3, GPT-4. No, then I think Grok or something, Twitter has come with a model. Then there's a model from, I think, Apple, which is called as Siri. Google has Gemini. So a lot of models are there. All these models are nothing but a set of matrix and vector operations which are put together in a graph format. Okay, you have all these operations put together in a graph format. That is what is a model. Now, whatever is the user input, now how it is realized as a model, for that you need something called as a graph compiler. Okay, so graph compiler is actually end to end. You get a use case, you will get a model which you can deploy it on the hardware. Okay, now all these graph compiler are called as an MLIR based compiler. Okay, MLIR is nothing but machine learning intermediate representation. Okay, the difference between your GCC compiler or Java compiler to MLIR is the intermediate representation in this graph compiler is actually different. Okay, so in a GCC compiler, you will have add, mul instructions. So in your GCC or Java compiler, you will have the intermediate representation based on this. But in a graph compiler, the intermediate representation will be based on this. Okay. Now, if someone can visualize this kind of a representation into this kind of a representation on the right side, right? Or this for loop he can realize as like this, right? Then he is very good in graph compilers. Okay. He has an understanding. Of course, the subject is always deep. There is a lot to learn. Okay. So OpenCL, TensorFlow, PyTorch, CUDA, I think all these you would have heard. All these are some of the compilers. Okay. All these have a lot of job opportunities in the market. Problem is we don't have the skill set matching. Okay. The skill set matching is much worse in Western countries. Okay. Yeah. So then the last thing about this, no, the accelerators or the modern high powerful machines is that we have to use all the features that are there in the uh, complete software life development cycle. For example, you have compilers. Compilers will have some compiler intrinsics whereby you can say, no, you have to take this function in a different way. You should take these following C code as a SIMD instruction. Like that, you should give some instruction to the compiler at compile time, which will actually generate the code that will perform better on the hardware. Okay. Now, if all, then you have something called as the optimizations in GCC compilers like O3, O2. You have to you can specify exactly what kind of an architecture, whereby we can actually make the binary that is generated for these applications very very uh, perfect. I would say perfect or much closer to the hardware. Okay, so the worst case is if everything happens but still you need much more performance, if your throughput is not informing or your image rendering, the image rendered video or audio is not clear, the clarity is not good, you should get into writing assembly language as a last option where you can actually improve the performance. Okay, for example, this OpenMP actually has some macros which actually helps in doing memory parallelism. Okay, for certain pieces of your code, you can mention these pieces of code, you can use memory parallelism. Okay, so these are something which we have learned and we have to implement. Now, see, when we face an interview, how one candidate performs and better than other candidate, although they have similar CGPA, they have very similar entrance scores, marks. That's because the second candidate is able to apply whatever he has learned as an improvement over the existing solution. So these are some improvements which we should learn and we should use to actually realize the complete potential of the hardware. So the final thing is, I kind of got an image where how things are inside, how we should see is whatever you see here, this is a complete product software. Okay, for any image application, video rendering, AI/ML, deep learning, all GPUs, neural processing units, everything will have this. Will come out like this, a complete product. Now, as an engineer, we need to figure out what are the parts of the product. So all these are different parts of the product. Okay. So this is, let's say, platform software. These are different applications, compiler that is needed to develop the product, and this is the network. Okay, this is that AI/ML network or model. Okay, your ChatGPT model. Okay, now from a platform development perspective, what happens is, right, this is seen as a complete product from outside. It's a square. Actually, it is not a square. It is something like this. There's a big hole. Okay, inside this big hole is where your network fits in. When your network fits in and you say the system to start running, immediately there will be some software routines which will actually start consuming the network, which will actually do some matrix vector operation on the hardware, and the result will come outside this and it will be taken out for processing by the applications. Okay, so see, if someone can see things like this in a very simple way, no, they will understand full thing. Okay, see, the most important thing for anyone writing a C program, even you write a hello world program or any simple function, you should ask a question: who calls the main function? If you have asked this question to you in the first year or whatever time, no, if it strikes your mind, that's actually the point in time in your career you are actually starting to learn the subject truly. You're actually personally you're making an attempt to master the subject. Okay, so we should ask fundamental questions to ourselves to actually understand whatever the big technology changes that are happening. If someone knows the answer how main function works, in a C program, he will know how this network big chat GPT model actually runs in the hardware, right? So I'll stop at this point. So these are some reference links. I'll share the slide. If you want, you can just go through this. You can use as a starting point to explore more. So I'm open to questions now. So, so I'll just get my camera switched on since the presentation is over, right? I think bandwidth should not be a problem.
Mike, sir?
Yes, sir.
Personal